Welcome to Calm and Clever. It's lovely to have you here tonight. So before we begin, let me ask you something the way I always do. Where in the world are you watching from? Wherever you are right now, whatever corner of the night you've folded yourself into, I'm glad you came. Maybe you're lying in bed with the blanket pulled up to your chin. Maybe there's a lamp still on somewhere across the room, throwing a soft little pool of yellow light onto the wall. Maybe you're on a train, or a couch, or curled in a chair with a mug of something warm going slowly cold beside you. It doesn't matter. You're here, and that's enough. Settle in, and if you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who've already subscribed, who come back night after night, thank you. Truly, you're the reason there's a tomorrow night at all. Now tonight we're going to drift up and out, away from the lamp and the blanket and the warm mug, all the way out past the planets, out among the stars. We're going to go looking for the biggest ones, the largest stars anyone has ever found, and I'll be honest with you straight away the way a friend should be. I hope this isn't so interesting that it keeps you awake, but if it does, well, at least you'll have learned something lovely on the way. A fair trade, I think. And here's the gentle truth of it, so you can let go of any pressure right now. You do not have to follow every number. You do not have to hold every name in your head. If you drift off somewhere in the middle of all this, before we even reach the biggest one, that's perfectly fine. The stars will still be there. They've waited millions of years already. They can wait for you. We're going to move slowly tonight, softly, one idea at a time, no rush at all. So if your eyes start to close, let them. Let's begin, shall we? I want to start with a number, just one, and it's a friendly one. So don't tense up. Our own sun, the star we know best, the one that warms your face on a good afternoon, has a radius of about 696,000 kilometers. That's the distance from its center out to its glowing surface. 696,000 kilometers. It's an enormous number, of course, far too big to really feel. You could line up more than 100 Earths across the face of the sun and still have room to spare. So let's not even try to picture the kilometers. Let's just give that number a name and a shape. We'll call it one solar radius, one sun's worth of width out from the middle. That's our measuring stick for the whole night. Everything we talk about, every giant we meet, we'll measure it in suns. How many suns wide is it? That's the only question. Hold that picture, one sun sitting where it sits, 93 million miles away, warming the morning. Now I want you to imagine something. Imagine we could reach out and pluck the sun right out of the sky, lift it gently out of the center of everything, and set down a different star in its place. A famous one, a red supergiant called UY Scuti. It lives in a small, faint constellation called Scutum, which is Latin for the shield. You'd struggle to find it with your eye. But for most of the last decade, this was the star, the one all the videos pointed to, the largest star ever found. So picture it. We've taken away our gentle little sun, and in its place we've set down UY Scuti. And for a long time, the measurement everyone trusted said that this star was about 1,700 times wider than the sun, 1,700 solar radii. Let that wash over you slowly, not one, not 100. 1,700 suns laid edge to edge would only just reach across its face. What does that actually mean, sitting where the sun sits? It means the surface of this star, the glowing outer edge of it, wouldn't stop where the sun stops. It would keep going. It would swallow the orbit of Mercury, that little scorched world closest in, gone somewhere deep inside the star. It would swallow Venus, our bright, cloudy neighbor. It would swallow the Earth. You, your bed, your lamp, your warm mug, all of it somewhere inside the glowing body of this one star. And it wouldn't even slow down there. It would swallow Mars, the red one, and it would keep reaching outward, out across the Great Gap, out past where the asteroids drift, reaching and reaching until its surface stretched toward the orbit of Saturn, the ringed planet. So far from the sun that sunlight out there is thin and cold and pale. All of that. The whole inner solar system and most of the outer one tucked inside the body of a single star with room to spare. That's the picture the size comparison videos love, the dizzy, swooning scale of it. And it is a beautiful picture. There's a reason it makes people gasp. But here's where the story gets quietly strange. And this is the part most of those videos never tell you. The part I find far more interesting than the bigness itself. So, stay with me, softly. That star, UY Scuti, was crowned the largest known star back in 2012. Astronomers using a telescope in Chile measured it, and the number came back at around 1,700 suns, and the headlines wrote themselves, "The biggest star ever found." And for years that's what everyone said. And then, slowly, that crown began to slip. Because here is the thing about UY Scuti that nobody put on the posters. Today, many astronomers think it isn't 1,700 suns wide at all. They think it might be closer to 1,000. Some estimates push it lower still, down towards 750. Less than half of what we once believed. The biggest star, it turns out, may be barely half the size we crowned it. Now stop and sit with how odd that is, because the star didn't change. UY Scuti didn't suddenly deflate. It didn't lose weight or shrink in the night. It is doing exactly what it was doing in 2012, exactly what it was doing 1,000 years before that, burning and pulsing away out there in the constellation of the Shield, completely indifferent to us. The star never moved. The star never shrank. We changed. Our measurement changed. We got better at looking. And to understand how that can happen, how a star can lose half its size on paper without anything happening to the star at all, you have to understand one quiet, humble little fact about how we measure these things. And it's the secret heartbeat of this whole video, so let me lay it down gently. We cannot just hold a ruler up to a star. Obviously, they're impossibly far away. So how do we figure out how big one is? Well, it comes down to two things multiplied together. First, how big the star looks in the sky. The tiny angle it spreads across, the apparent size, the way a coin held at arm's length looks bigger than the same coin held across the room. And second, how far away it actually is. You take how big it looks and you stretch it out by the distance, and that tells you how big it truly is. That's the whole trick. The real size of the star is its apparent size multiplied by its distance. Think of it like a shadow on the wall from a candle. A small object held close to the flame can throw a huge shadow. A bigger object far away can throw a small one. If you only see the shadow, you can't know the true size of the thing, not until you know how far it stands from the light. The distance is everything, and here's the trouble. The distance is exactly the thing we're worst at knowing, because the moment your guess about the distance is wrong, your guess about the size goes wrong with it, and it goes wrong twice as hard. If you think a star is farther away than it really is, you'll think it's a giant, because for it to look as big as it does from way out there, it would have to be enormous. But pull it closer, decide it was nearer all along, and suddenly the same little smudge of light in the sky doesn't need to be a monster anymore. It can be modest, ordinary. The number collapses just like that. So what happened to UY Scuti? What knocked it off its throne? A spacecraft, a quiet, patient spacecraft, drifting out in space with one job. It's called Gaia, run by the European Space Agency, the ESA. And Gaia spent years doing nothing but measuring, with breathtaking precision, exactly how far away the stars are. Billions of them. It watches each star very carefully and notices the tiny, tiny way it seems to shift back and forth across the year as the Earth swings around the Sun, the same way a nearby tree seems to shift against the distant hills when you sway your head from side to side. That little shift tells you the distance, and the smaller and steadier you can measure that shift, the better you know how far away the star really is. And when Gaia turned its careful eye on these record-breaking giants, on UY Scuti and others like it, a lot of the old distances turned out to be off. And every time the distance got corrected, the size got corrected right along with it. Some of these famous giants got nudged a little closer. And as they came closer on paper, they got smaller. The shadow stayed the same. The candle just turned out to be nearer than we thought. So the biggest star isn't shrinking, we're just finally measuring the room properly. And I find something deeply calming in that, honestly. The idea that the universe wasn't lying to us, and the old astronomers weren't foolish. They measured as well as they could with the tools they had, and the moment we got a better ruler, the picture gently corrected itself. That's not failure, that's how it's supposed to work. The science breathing, settling, getting truer over time, like your own breathing right now, slowing down, finding its rhythm. And this isn't a one-time thing, this isn't just UY Scuti having a bad night. This is the whole pattern of the story we're going to tell tonight. Almost every giant we meet has had its size revised, argued over, knocked up and knocked down as the distances got better. The record holders keep trading places, the crowns keep slipping, and that's not the embarrassing part of the story, that's the beautiful part. So if you came here hoping I'd just tell you plainly what the single biggest star in the universe is, one clean number, no fuss, then I have to gently disappoint you. And I want to, because the truth is so much more interesting than the tidy answer. You see, when you first hear the question, what is the largest star ever found? It sounds like such a simple thing to ask, the kind of question that ought to have a simple answer, like asking, what's the tallest mountain on Earth? There's a fact-shaped hole there, and surely you just fill it in. Stephenson 218, UY Scuti, some name, some number, done, roll the credits. But the closer you lean in, the fuzzier the edges of that question get. And I mean that almost literally. Because it turns out that even the simplest part of the question, the word largest, doesn't have one clean meaning when you're talking about stars like these. We're going to find, before the night is over, that astronomers can't always even agree on where one of these stars ends. The surface, the edge, the place where you'd say, the star stops here and space begins there. That line isn't as solid as you'd think. We'll come back to that. It's one of the strangest, gentlest ideas in all of this, and I want to give it room when we get there. But for now, just hold the feeling of it. The question that sounded so simple has soft, blurred edges. There's no single number waiting at the end of tonight, no neat little trophy. Instead, there's something better. A whole landscape of giants, all of them uncertain, all of them being measured and remeasured, all of them leaning right up against the edge of what's physically possible. And there is an edge. That's the other half of the promise. And we'll get there in our own slow time. There's a wall, a line in physics that no star can cross. And the closer a star gets to it, the more it seems to throw itself apart. But that's for later, when you're deeper into the night. For now, let's get to know the kind of star we're even talking about. Because to understand why these giants are so huge and so strange and so soon to die, you have to understand what they are. And what they are is not what most people imagine. When you hear the biggest star, you probably picture something fierce, something blazing white hot, the brightest, hottest, most powerful furnace in the sky. A bigger version of the sun, only more so, more heat, more fury, more everything. But that's not it at all, and this is one of the loveliest little surprises in the whole subject. So let it land softly. The largest stars we know are not the hottest, they're some of the coolest. They glow a deep, sullen, sleepy red, the colour of dying coals in a fireplace at the end of a long evening. Where the sun's surface burns at around 5,500 degrees, these enormous giants are cool by comparison, simmering at only 3,000 to 4,000 degrees. Still hot enough to vaporize anything you can imagine, of course, but cool for a star. Cool enough to glow that gentle, embery red instead of a fierce white or blue. We call them red supergiants, and the very largest of them, the most swollen, the most extreme, we call red hypergiants. And the word supergiant is exactly right, but maybe not in the way you'd guess, because their hugeness isn't really about power, it's about puffiness, about bloat. Let me give you an image to hold. Imagine a hot air balloon. The fabric of a hot air balloon doesn't weigh very much. There isn't a lot of material there. But fill it with warm air and it swells up into something vast, something that can carry people up into the sky far bigger than the little basket beneath it. The size doesn't come from packing in more stuff. It comes from the same amount of stuff spread out, puffed up, filling an enormous volume with almost nothing in it. That's a red supergiant. It is a star that has puffed itself up to a tremendous size, but it is shockingly thin and wispy out near its surface, so low in density that if you could somehow scoop up a bucketful from those outer layers, you'd find almost nothing in your hand, closer to the emptiness of the air around you than to anything solid. These stars are mostly enormous, glowing, near vacuum, a fragile, swollen, sleepy red giant, hundreds and hundreds of times wider than the sun, but made of almost nothing where it's biggest. And here is the part that gives the whole thing its quiet weight, the part that turns this from a list of fun facts into something almost tender. These stars are huge because they are dying. That bloating that's swelling up into a hot air balloon the size of the inner solar system isn't how a star spends its life. It's how a star ends it. A red supergiant is a massive star in the very last chapter of its existence. For most of its life, it was smaller, hotter, fiercely burning hydrogen in its core, steady and bright and contained. But these are heavy stars, and heavy stars live fast. They burn through their fuel at a furious pace. And when the fuel in the core starts to run low, when the long middle of the star's life is ending, the whole star responds by swelling, by puffing out those vast, thin, cool outer layers into the dark. The bigness is the symptom, the hugeness is the sign of the end. So every single one of these giants we're going to meet tonight, every record holder, every contested champion is an old star in its final act. Some of them are shedding their outer layers right now, casting off their own skin in great, slow clouds. Some of them will not last much longer at all in the patient reckoning of the cosmos. They are the brightest, biggest things, and they are the most fragile, and they are nearly done. There's something almost unbearably gentle in that if you sit with it. The biggest stars in the sky are the ones closest to the end. And that's a good thing to carry with you as we go deeper, that the size we're chasing tonight isn't a measure of strength. It's a measure of an ending, a long, slow, glowing goodbye written in red light across the dark. Now, we already met one of them, didn't we, out in the constellation of the Shield. UY Scuti, our fallen champion, the star that lost half its size, not by shrinking, but by being measured properly at last. It's still a red supergiant. It's still genuinely enormous, whether it's 1,000 suns wide or 750. Either way, it would swallow the orbit of the Earth without a second thought. Its demotion from 1,700 down toward 1,000 didn't make it small. It just made it honest. It moved from being the undisputed king to being one giant among many, all of them jostling, all of them uncertain. And that constellation, Scutum, the Shield, is worth pausing on for a moment because it sits along a crowded, dusty lane of our own galaxy, the Milky Way. And that turns out to matter. enormously. Because the very thing that makes a region rich with these giant stars, all that gas and dust and crowding along the galactic plane, is the same thing that makes them so hard to measure. The dust dims their light and reddens it and muddles our sense of how far away they are. Trying to judge the distance to a star buried in that haze is a little like trying to guess how far away a street lamp is on a thick, foggy night. You can see the glow. You just can't quite trust how far off it is. And without the distance, remember, you can't trust the size. So there's a quiet irony sitting at the center of this whole subject. And I want to leave it with you as we drift toward the next part of the night. The most famous record-breaking giants, the ones whose names you'll have heard, the ones plastered across every size comparison video, are very often the ones we've measured the worst. They're buried deep in the dusty lanes of our own galaxy, where the distances are murky and the numbers wobble. The headline stars are the unreliable ones, and the stars we actually know the size of, really know with confidence, are quieter, less famous, tucked away in places where the distance is pinned down and trustworthy. We'll meet one of those later, a giant in another galaxy entirely, one we can actually believe. And it's the most beautiful one of all because in 2024, for the very first time, we got an actual close-up picture of it. But that's still a way off, deeper into the dark. For now, just rest in the strangeness of what we've found so far. That the biggest star isn't the hottest, it's the coolest. That its hugeness isn't strength, it's the swollen sign of an ending. That its size isn't packed and dense, it's puffed up and thin, a glowing balloon of almost nothing. And that the very crown of largest keeps slipping from one star to the next, not because the stars are changing, but because we are finally learning to measure the room they live in. The candle stays the same. We just keep getting nearer the truth of how far away it stands. So let's hold there for a moment. The lamp, still on maybe, somewhere across your room. The blanket warm. UY Scuti glowing its sleepy red out in the shield. 1,000 suns wide, give or take, dying slowly, indifferent to all of it. And a whole sky full of other giants still waiting for us, each one a little stranger than the last. We'll go to them soon. We'll meet the one you can see with your own naked eye if you know where to look. We'll meet the famous shoulder of the hunter, the star that made headlines around the world when it mysteriously dimmed. And we'll wander out eventually all the way to another galaxy, to the dying giant we finally photographed. There's no rush. The stars aren't going anywhere. Let's just keep drifting. Slowly, softly, one quiet mystery at a time. Let's begin where most of these stories begin, with a number so familiar that you've probably stopped seeing it. The sun. Our sun. The one that warms the side of your face on a slow afternoon. Across its middle, from one edge to the other, it measures about 696,000 kilometers. Hold that number loosely. You don't have to memorize it. You just have to feel it as the ruler, the one yardstick we'll lay against everything else tonight. Because every star we meet, every swollen giant out there in the dark, will measure in suns. So many suns wide. Picture it as a single coin, and we'll be stacking those coins in your mind until the stack gets almost too tall to think about. Now take that ruler and walk it out to UY Scuti, out in the constellation Scutum, the Shield, a red supergiant. For most of the last decade, this was the star, the one in every animation, every zoom, every little gasp of an internet video. Back in 2012, astronomers measured it at around 1,708 times the width of the Sun. And here is where you let the scale device do its slow, gentle work. Imagine, just for a moment, pulling our own Sun out of the center of the solar system and setting UY Scuti down in its place. Its glowing red surface wouldn't stop at Mercury. It would swallow Mercury whole as if the little planet were a pebble dropped into a furnace. Then Venus. Then Earth, the ground beneath you. The lamp across your room, all of it inside the star. Then Mars. And still the surface would keep going, out and out, reaching toward the orbit of Saturn. A single star wide enough to drink the inner solar system and most of the outer one too. That's the picture that built the legend. And it's a beautiful picture. So before we go any further, let me say the things I always like to say at the start. There is no need, none at all, to hold on to every number tonight. If a figure slips past you, let it slip. If your eyes are already heavy, let them close. The stars will still be here, glowing patiently, whether or not you remember exactly how many suns wide any of them are. This isn't a test, it's a place to rest. We're going to move slowly through all of this softly, one quiet idea at a time, and the only thing I'd ask of you is to get comfortable. Pull the blanket a little higher if you have one. Let the back of your head sink into the pillow. If you drift off somewhere in the middle of a dying star, honestly, that might be the nicest possible place to fall asleep. And while we're settling in, welcome. Welcome to Calm and Clever. If you enjoy these slow journeys out into the dark, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think, and I'm grateful for every single one of you who's already here. So thank you, truly. And while you're getting comfortable, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the dark? Leave it down below if you feel like it, and drift off whenever you need to. Now, back to UY Scuti and to the first small surprise of the night, because that magnificent number, that 1/708 suns that reach all the way out to Saturn, well, it isn't really true anymore. And here's the strange part. The part that I think is the whole quiet heart of this story. The star didn't shrink. Nobody nudged it. Nobody let the air out of it. It is exactly the same star it was in 2012, glowing the same sleepy red, doing the same slow, dying it has been doing for thousands of years. What changed wasn't the star, what changed was us. You see, you can't just look up at a star and read its size off the sky. A star, even a giant one, is so unimaginably far away that it appears as the tiniest possible smudge of light, a dot, a grain. To know how big it actually is, you need two things. You need to know how big it looks, that little angle it takes up in the sky, and you need to know how far away it is. Multiply those together, the apparent size and the distance, and only then do you get the true size. It's a little like judging how big a candle flame is from across a dark field. If you think the candle is close, you'll guess it's small. If you suddenly learn it's twice as far away as you thought, then to look that same size, it must be twice as large. The flame never flickered, your sense of the distance did. And distance, it turns out, is the hardest thing in all of this to pin down. For a star like UY Scuti, buried deep in the crowded, dusty plain of our own galaxy, the distance was always a bit of a guess. A reasonable guess made by careful people, but a guess. So when a spacecraft called Gaia, launched by the European Space Agency, set about doing nothing but measuring the precise positions and distances of more than 1 billion stars, with a delicacy nobody had ever managed before, it began quietly rewriting the numbers. And UY Scuti's distance came out different than everyone had assumed, which meant its size had to come out different too. The new estimates don't put it anywhere near 1,708 suns. They tend to land somewhere closer to 750, maybe 1,000 times the width of the sun. Still vast. Still enough to make our own star look like a spark, but no longer the undisputed king. The crown slipped off, not because the star moved an inch, but because we finally measured the size of the room it's standing in. I find that oddly comforting lying here in the dark. The idea that the universe wasn't lying to us. We just hadn't learned to see clearly yet. And we're still learning. that's not a flaw in the story. That is the story. Which brings us to a question that sounds like the simplest one in the world. What is the largest star? It feels like the kind of question that ought to have a clean answer, a single name, a single number, the way "what's the tallest mountain" has an answer. You'd expect to be able to point at one star and say, "That one, that's the biggest, done." But the closer you lean in, the fuzzier the edges of that question become, not just because the rankings keep shifting as our measurements improve, but because these stars, the very biggest ones, don't really have a clean edge to measure in the first place. Hold that thought gently. We'll come back to just how strange that is, the idea that astronomers can't quite agree on where one of these giants even ends. For now, let's understand what kind of star we're even talking about. Because the giants on this list, every one of them, belong to a particular peculiar family. They are red supergiants, and their grander cousins, the red hypergiants. And the first thing to know about them, the thing that turns everything you'd expect upside down, is that they are cool, not cold of course, but cool for a star. Their surfaces simmer at something like 3,000 to 4,000 degrees, where our own sun's surface burns nearer to 6,000. That deep ember red you imagine when you picture UY Scuti, that's the color of a star that has, in a sense, started to cool down toward the end. And that's the heart of it. Their enormous size, that swollen, planet-swallowing vastness, isn't a sign of strength, it's a symptom. It's the look of a star that is dying. Here's the gentlest way I can put it. A star spends most of its long life in a careful balance. Gravity is forever trying to crush it inward, to squeeze it down into a point. And the furnace at its core, fusing hydrogen into helium, pushes outward, holding gravity off. For most of a star's life, those two forces sit in a quiet truce, and the star stays roughly the same size for billions of years, patient and steady. But the biggest, most massive stars burn through their fuel at a furious pace, and when the core begins to run low, when that delicate truce starts to break, something surprising happens. The outer layers don't collapse, they swell. The star puffs up enormously, its surface ballooning outward across hundreds of millions of kilometers, growing cooler and redder and thinner as it goes. So a red supergiant isn't a star in its prime, it's a star in its final act. Bloated, low in density, so puffed out that if you could somehow scoop up a handful of its glowing red surface, it would be thinner than the air in your room, closer to a vacuum than to anything you'd call solid. A glowing balloon of almost nothing, stretched to a width that would swallow worlds. And this phase, this vast red dying, is brief, by the standards of the cosmos, just a flicker at the end of a fast and furious life, which is its own kind of strange, gentle truth to carry towards sleep. That the largest things we've ever found out there aren't the strongest, or the youngest, or the most full of fire. They're the ones nearest the end. The size is the sign of the ending, the sign. And out in the shield, in Scutum, UY Scuti is doing exactly that right now, glowing its sleepy red, swelling toward its own quiet conclusion, 1,000 suns wide, give or take, while we lie here and watch. And yet, if you ask astronomers to tell you exactly how wide UY Scuti is, right now, tonight, they will pause. And that pause is interesting, because the story of measuring these giants turns out to be almost as strange as the giants themselves. Here is the difficulty. When you look at a star, even through the most powerful telescope ever built, almost no star appears as a disk. They are simply too far away. The sun from Earth spans about half a degree of sky, wide enough to blind you, wide enough to cast sharp shadows on a summer afternoon. But every other star, even the closest ones, the red dwarfs huddled a handful of light years away, are pinpoints. Geometry compresses them to nothing. A single point of light is all you get, however large the telescope, however perfect the mirror, because the distance is just too immense. The largest known supergiants, the ones on this list, subtend angles on the sky of only a few milliarc seconds. A millisecond. A degree of sky is divided into 60 arc minutes, and each arc minute into 60 arc seconds. A milliarc second is 1,000th of that. It is the angle subtended by a coin sitting on a table roughly 20 kilometers away from you. Seeing that coin resolving its edge from its center, telling exactly how wide it is not something a conventional telescope can do. The atmosphere alone blurs things far worse than that, and yet astronomers need to measure exactly that angle if they want to know how physically large a star is. This is where interferometry comes in. Instead of a single giant mirror, interferometers combine the light gathered by multiple telescopes separated by large distances, sometimes hundreds of meters, sometimes kilometers. The separation itself acts as the effective aperture. The Very Large Telescope Interferometer, the VLTI, operated by the European Southern Observatory in the Atacama Desert of Chile, does exactly this, combining the light from multiple telescopes into a single measurement sharp enough to resolve those milliarc-second angles. So does the CHARA Array, the Center for High Angular Resolution Astronomy in California, which uses 6 telescopes spread across Mount Wilson to achieve resolutions finer than any single mirror could manage. And gravity, a remarkable instrument mounted at the VLTI, pushes this even further, combining 4 of the VLT's unit telescopes with extraordinary precision. These are the instruments that have actually measured the angular sizes of the largest known stars, not estimated, not guessed, measured in the most direct sense available to us. But here is the catch. The angular measurement alone is not enough. Angular size tells you what fraction of the sky the star covers. To turn that into a physical size, a real radius in kilometers or in solar radii, you need to multiply by the distance. And for most of the stars on this list, the distance is exactly what we don't know well. Think of it this way. Imagine you're trying to figure out how tall someone is, but all you can measure is the angle they subtend from where you're standing. If they're 1 meter away, that angle means they're quite short. If they're 10 meters away, the same angle means they're very tall indeed. Same angle, completely different answer depending on the distance. The distance is everything. For stars in the galactic plane, buried behind clouds of interstellar dust, crowded among millions of other stars, distances are genuinely difficult. Parallax, the gold standard method that measures how a nearby star shifts position against the background as the Earth moves around the Sun, works beautifully for nearby stars but becomes increasingly uncertain at the distances of these remote supergiants, hundreds or thousands of light years away, where the annual parallax shift shrinks to a tiny, hard-to-measure wobble. This is where Gaia changed things. The European Space Agency's Gaia mission, launched in 2013, has spent years measuring the positions and parallaxes of over 1 billion stars with unprecedented precision. Gaia's data releases have quietly but persistently forced astronomers to revise the distances to dozens of famous supergiants, and those distance revisions drag the size estimates with them, because radius depends on distance in a very direct way. If Gaia says a star is closer than previously thought, the radius shrinks. If it says the star is farther, the radius grows. The measurement of the angular size may not have changed at all, but the star's apparent size in our ledger shifts simply because our understanding of its position in space improved. And there is a second path to stellar radii, one that doesn't require directly resolving the disk at all. If you know a star's luminosity, how much total light it pours out each second, and you know its surface temperature, you can calculate its radius from the laws of blackbody radiation. The relationship is elegant and well established. Luminosity scales with the radius squared, and the temperature to the fourth power. A star that is cool but enormously luminous must mathematically be enormous in radius, because cool surface temperatures mean lower energy output per square meter, so you need far more square meters to account for all that light. This is why the cool, red supergiants dominate the size rankings. Their low temperature means their radius has to be colossal to explain their brightness. But this second method also inherits distance error, and it inherits it twice. Luminosity is inferred partly from distance, and distance uncertainty feeds into the radius calculation not once, but as a squared term. A 20% error in distance can translate to a 40% or more error in radius. These are not small corrections. And then there is a third complication, a subtler one, and it is this. These stars don't actually have a clean, well-defined surface. The Sun's surface, the photosphere, is a relatively sharp transition. Within a few hundred kilometers, the plasma goes from opaque to transparent, and that thin layer is what we call the surface. It is well defined enough that a solar radius around 696,000 kilometers is a number that means something precise and consistent. The red supergiants are different. Their outer layers are enormous, extended, and in constant turbulent motion. Giant convective cells, each one potentially as large as the entire Sun, bubble up from the interior, carrying heat toward the surface, and then subsiding. The outer atmosphere blurs into a vast, pulsating, semi-transparent envelope. Different wavelengths of light escape from different depths within this envelope, which means the star looks different sizes depending on what color of light you use to observe it. Astronomers use a specific technical definition called the Westerlund radius, which corresponds to a particular optical depth within the stellar atmosphere, a layer where the mean free path of a photon reaches a defined threshold. But below that layer, further out, there is an extended envelope of molecules and dust. And if you measure the star's apparent size at infrared wavelengths, which probe the dust-forming regions far from the core, you may get a radius significantly larger than if you measure at optical wavelengths. So when someone asks how big UY Scuti is, they're actually asking multiple questions at once. Big according to which measurement technique, big at which wavelength, big according to which distance assumption, and these are not trivial differences. They can account for discrepancies of hundreds of solar radii in the quoted figures, which is the equivalent of disagreeing on whether something is the size of a house or the size of a city block. This is not a failure of astronomy, it is astronomy being honest. The fuzzy surface of a red supergiant is genuinely fuzzy. The star itself doesn't have a clean edge. And saying so, understanding why, carrying that intellectual honesty into the rankings, is what separates a real understanding of these giants from a simple size reel with confident numbers and no caveat. So when you hear a figure for any of these stars, hold it loosely. It's a real measurement of a real thing made by serious scientists with remarkable instruments. But it comes wrapped in assumptions chiefly about distance, and those assumptions are still being refined. With all of that in mind, let's meet the first of our ranked giants and do it justice. Number 6 on our list is a star you can, under the right conditions, see with your own eyes. On a clear night, away from the lights of a city, with dark adapted eyes and a steady gaze, you can look toward the constellation Cepheus, the King, that dim pentagon of stars near the north celestial pole, circling endlessly around Polaris, never setting for anyone at northern latitudes. And somewhere within it, a small, deeply colored point burns. Not bright, not prominent, not the kind of star that immediately grabs you. But if you know where to look, it glows a remarkable deep red, a warm, smoldering garnet color, unlike almost anything else in the sky. This is Cephei, William Herschel, the great 18th and 19th century astronomer who built his own reflecting telescopes, who discovered Uranus in 1781, who catalogued thousands of nebulae and double stars, who spent decades mapping the structure of the Milky Way himself. This careful, methodical observer looked at this star and was moved to give it a name beyond its catalogue designation. He called it the Garnet Star, not a technical name, not a designation, a name drawn from color and beauty. The Garnet Star. Herschel was not wrong. The deep red of Cephei is the color of a star that has swelled so enormously that its surface temperature has dropped to somewhere between roughly 3,000 and 4,000 Kelvin. That's cooler than almost any other type of stellar surface. At that temperature, the star emits most of its light at wavelengths your eye registers as red and orange, and very little in the blue. The result is that unmistakable warm glow. Cephei is classified as a red supergiant, and it is one of the largest stars close enough to study in reasonable detail. Estimates of its radius vary, as they always do with these objects, but figures in the range of roughly 1,000 to 1,400 solar radii appear consistently in the literature. At the lower end of that range, 1,000 solar radii, each of those radii being 696,000 kilometers, you are talking about a sphere whose diameter is roughly 1.4 billion kilometers. The Earth orbits the Sun at a distance of about 150 million kilometers, so Cephei, placed where the Sun is, would engulf the inner solar system entirely, its surface reaching well past the orbit of Earth. At the higher estimates, it would reach past Mars and continue outward into the asteroid belt toward Jupiter. It is also misbehaving in the way these extreme stars tend to. Cephei is a semi-regular variable, which means its brightness fluctuates over time, not in a perfectly predictable clock-like way, but in a roughly cyclic pattern with periods of hundreds of days, driven by pulsations in its outer layers. Those great convective bubbles of plasma rising and falling on the star's surface create pressure waves that pass through the star's atmosphere, and those waves change the star's apparent size and brightness in cycles. The star breathes, in a manner of speaking, slowly and irregularly. This pulsation is one of the reasons size measurements for Cephei come with such a wide range. The star is not the same size at all times. It is genuinely varying, and the pulsations are linked to the mass loss the star is undergoing, shedding its outer layers into space in slow, steady outflows, the same process happening in all these dying giants, the process that is slowly but surely reducing them. Cephei is expected to end its life as a supernova, though on a time scale that to human ears sounds impossibly far, but in astronomical terms is genuinely imminent, within the next 100,000 years or so, perhaps sooner. When it goes, it will briefly be visible in daylight from Earth, a stark, sudden point of light in the constellation of the King, burning for weeks. But tonight, it's just a quiet garnet point in Cepheus, visible to the patient naked eye. The only record-class giant on our list you can see without a telescope. There is something quietly remarkable in that. All of this, the scale, the dying, the measurements argued over in journals and corrected by satellites, available to any human being who steps outside on a clear night and knows where to look. Now, before we move further up the list, we should spend a moment with two stars that didn't quite make the top 7 by sheer size, but that most people have already heard of, because they serve as the best possible on-ramp to understanding what the larger, less familiar stars above them are actually doing. These two are the stars that most people mean when they think of the word supergiant, the famous ones, the ones with names that don't require a catalogue number: Betelgeuse and Antares. Antares first, briefly, because it illustrates the scale so cleanly. Antares sits in the constellation of Scorpius, the Scorpion, one of the more recognizable star patterns in the southern sky during summer evenings in the northern hemisphere. The name Antares comes from the Greek, meaning roughly the rival of Ares, rival of Mars, because its deep red color and moderate brightness make it easy to confuse with the planet when Mars happens to pass nearby. Ancient Greek astronomers noticed the resemblance and named the star accordingly, a celestial impersonator catching someone's eye across millennia. Antares is a red supergiant, with estimates typically placing its radius somewhere around 680 to 700 solar radii. At 700 solar radii, its surface, if placed at the Sun's location, would extend to roughly the orbit of Mars. It is one of the larger stars in our immediate corner of the galaxy, brilliant enough to be easily visible to the naked eye as a distinct orange-red point in the Scorpion's heart. And yet it sits comfortably below the top 7 in this counting. It is, for all its impressive size, solidly mid-table in the company we're keeping tonight. Betelgeuse is more famous, and for good reason. It marks the left shoulder of Orion, one of the most recognizable constellations in the northern winter sky, and its deep red-orange color stands out even in moderately light polluted skies. On a clear winter night, you can find it without any effort at all, a warm, slightly fuzzy-looking point at the upper left of the hunter's outline. Its radius estimates have shifted over time, as with all these giants, but it currently sits in the range of roughly 700 to 900 solar radii, depending on the measurement method and wavelength. Like Antares, it doesn't crack the top 7 by size, but it matters here for a different reason entirely. In late 2019, Betelgeuse did something nobody expected. It began to dim. Not slightly, not in the way that normal variable stars dim and recover in predictable cycles. It dimmed dramatically, dropping to about 60% of its normal brightness over the course of several months, fading enough that casual observers noticed, and astronomers started paying very close attention. By February 2020, it had reached the lowest brightness ever recorded for it in the modern era of precise photometry. The internet did what the internet does, and a significant number of headlines speculated breathlessly about whether Betelgeuse was about to go supernova, whether Orion was about to lose a shoulder, whether Earth was in danger, whether you could go outside right now and watch a dying star. The speculation was understandable. This was genuinely unusual stellar behavior, and supernovae are genuinely preceded by instability, but it wasn't a supernova. What the Very Large Telescope's imaging subsequently showed was something almost more interesting in a different way. A massive cloud of dust ejected from the star's surface in a convective event had cooled as it expanded outward and formed a kind of obscuring shell on one side of the star. The dimming wasn't the star's luminosity decreasing. The star was still pouring out the same light, but between us and that light sat a newly formed cloud of its own expelled material, blocking a portion of what we received. Betelgeuse had literally coughed up part of its outer atmosphere, cooled it into dust, and sent it drifting outward. And for a few months, that dust stood between us and the full glory of the star's light. When the dust cleared and dispersed, Betelgeuse brightened again, roughly back to its usual range. The great dimming, as it came to be called, was over, but what it revealed was a star in genuine, dynamic, active mass loss, not a quiet, passive shedding over eons. An active, episodic ejection of material, vivid and measurable, happening on timescales of months that humans could watch in near real time. This is what all the stars higher on our list are also doing, in various degrees. Betelgeuse is perhaps the most watched, the most famous, the one whose behavior got the most eyes on it, but the process, shedding mass, expelling the outer layers, slowly dismantling itself under its own internal pressures, is the common thread running through every star on this list. And Betelgeuse will go supernova, not tonight, not in any human lifetime, not in any span that the word soon means anything in daily experience, but within the next roughly 100,000 years, possibly much sooner in astronomical terms, likely far sooner than the Sun's remaining lifetime, it will exhaust its fuel and its core will collapse, and the outer layers will be flung outward in a blast visible from Earth in broad daylight, a new star briefly blazing in the shoulder of Orion, then fading over weeks and months to nothing visible. When that happens, an enormous expanding shell of gas and dust, enriched with the heavy elements forged in the star's core, iron, nickel, silicon, magnesium, oxygen, will spread outward into the surrounding interstellar medium, eventually mixing with other gas clouds, eventually seeding future star-forming regions with the raw material for new stars, and potentially for the planets that might form around them, and potentially for the chemistry that might eventually produce something like you. But that is getting ahead of where we need to be tonight, because further up the list, the behavior gets more extreme. The mass loss becomes more violent, the instability becomes more dramatic. And we begin to find stars that have been actively caught in the act of something more spectacular than a dimming episode. Number 5 on our list sits in the constellation of Cepheus as well, that same northern pentagon of stars. Its name is RW Cephei. It doesn't have a common name like Betelgeuse or Antares, no warm nickname from ancient observers, just a catalogue designation. But it earned the attention of astronomers in a remarkable way in the years 2022 and 2023. RW Cephei is classified as an orange hypergiant, or sometimes a red hypergiant depending on the specific temperature estimate and classification scheme used. The distinction between a supergiant and a hypergiant is not rigid, but hypergiants are generally understood as the most extreme, most luminous, most massive examples of the evolved giant phase, stars operating so close to the physical limits of what a star can sustain that they are inherently unstable. They are not just large, they are large in a way that their own physics is barely containing, barely holding together. Estimates of RW Cephei's radius range from roughly 900 to 1500 solar radii, a range that is itself telling. That 500 solar radius spread in a single object's quoted size reflects genuinely how difficult these measurements are and how variable the star itself may be. At 900 solar radii, it comfortably exceeds Betelgeuse. At 1500 solar radii, it approaches the scale of the largest objects in the known universe of stars. Somewhere in that range, on some night, is the true size of RW Cephei, and the uncertainty is honest. But what made RW Cephei remarkable in 2022 and 2023 wasn't a new measurement of its size. It was something it did. The star dimmed, significantly, dramatically, in a way that recalled Betelgeuse's great dimming, but in some ways more extreme. Astronomers with instruments on the Cara array were able to observe RW Cephei's surface in angular detail, and what they saw was striking. One portion of the star's visible surface appeared dramatically darker than the rest, a cool, dim region that astronomers interpreted as evidence of a massive convective event, a giant upwelling of material from the interior, similar in mechanism to the Betelgeuse event but on a scale commensurate with the star's more extreme nature. The dimming was interpreted as the visible signature of an enormous ejection of material from the star's surface, a mass loss event unfolding in more or less real time. A star that is too large, too luminous, too close to the physical limits that regulate what a star can sustain, shedding parts of itself. Not violently and instantaneously, as a supernova eventually will, but in these great episodic exhalations, each one carrying away mass and energy and complexity into the space around it. RW Cephei is thought to be in an extremely advanced evolutionary stage. It has already moved past the red supergiant phase in some respects, or is oscillating at the edge of it, potentially cycling back and forth between different configurations as its interior structure and energy generation shift. These hypergiant stars don't follow a simple, linear path to the end. They oscillate, they pulsate, they shed, they brighten and dim on irregular schedules because they are operating at the very edge of what stellar physics allows. Think of it as walking along the rim of something. Most stars walk through their lives in the quiet interior, well away from any edge. A red supergiant is already closer to the rim than most, but a hypergiant like RW Cephei is right there at the edge, and the wind is strong, and every now and then it stumbles slightly, catches itself, sheds a little mass to stay on its feet, and keeps going. How long it keeps going is something astronomers genuinely don't know with precision. These objects are rare enough and evolve on short enough timescales that we don't have many examples to work from, and the ones we do have are all different, all caught at different stages of a complex non-linear death. RW Cephei might go supernova relatively soon. It might shed enough mass first to become something different, a Wolf-Rayet star perhaps, a hot, compact, ferociously windy object stripped down to its bare core after losing most of its outer layers. The details depend on exactly how much mass it started with, exactly how much it has already shed, and exactly how fast it continues to shed. What is clear is that it is not stable, and that instability, that active, documented, directly imaged instability, is exactly why it belongs on this list. It's not just a number in a catalogue, it's a star that was caught in our lifetimes in the act of throwing itself apart. And that theme, stars that are large partly because they are in the process of losing mass, actively expanding their outer envelopes and shedding material into space even as their listed radii suggest an almost inconceivable size, that theme runs through the rest of this list, up to and including the very largest candidates we know. The larger they are, the closer they sit to the edge. The closer they sit to the edge, the more dramatically and actively they behave. There is something in that pattern worth sitting with for a moment. These aren't simply big things, they are big things that are, in a physical, documented, measurable sense, in the process of falling apart. The size is not a sign of strength or stability. It is a sign that the processes holding them together are strained, that the balance has shifted, that the final chapters are underway. You are made, every atom of you, of material that passed through stars that once upon a time looked roughly like this. Not necessarily this extreme, not necessarily this large, but the same general kind of object. A massive star in its final phases, swollen and shedding, eventually collapsing and exploding, flinging its contents outward. The iron in your blood was forged in stellar cores. The oxygen you breathe was synthesized in the nuclear burning shells of dying giants. The calcium in your bones, the carbon in your cells, all of it passed through something that once glowed red and enormous and then one day let go. And right now, tonight, RW Cephei in Cepheus is doing that. Dimming, swelling, shedding, balanced on its edge, enormous and unstable and quietly magnificent, several thousand light years away and yet made of the same physics, the same forces, the same fundamental balance between gravity and light and heat that makes everything in the universe what it is. Let's go just a little further, because above RW Cephei, the stars get stranger and the uncertainty in their sizes gets in some ways even larger, not smaller. And that is where the most interesting stories in this list live. The next stretch of the countdown is where the headline champions sit, the names that dominate the size comparison videos, the stars with the largest quoted radii in the literature. And it is precisely here that the question of how to measure a star honestly becomes most important, because the stars with the most impressive numbers are not, in general, the stars with the most reliable numbers. There is a reason for this, and it goes back to what we said about distance. The most famous, most cited candidate for the title of largest star, the ones with radii exceeding 2,000 solar radii, are Milky Way stars, sitting at large distances within the galactic plane. And the galactic plane is, from an astronomer's perspective, a difficult neighborhood. The plane of the Milky Way is dense with stars, gas, and dust. Interstellar dust between us and a distant star absorbs and scatters its light, making the star look dimmer than it really is. This reddening and dimming, called interstellar extinction, has to be corrected for when you calculate luminosity. But how much dust is there along any particular line of sight? That's not perfectly known. You can estimate it from models of the interstellar medium, from the observed colors of the star, from ancillary measurements of the interstellar absorption at different wavelengths. But those corrections carry their own uncertainties, and those uncertainties feed directly into the luminosity and radius estimates. Parallax measurements of distant supergiants in the galactic plane are hard because at distances of several thousand light-years, the annual parallax shift is extremely small, smaller than the precision achievable for many targets even with Gaia, which has pushed the frontier further than any previous mission but has not eliminated the difficulty entirely. And for stars embedded in rich clusters or surrounded by nebulae, crowding makes the photometry more complex still. So you end up in a situation where the most extreme-sounding numbers come attached to the least certain underlying measurements, and the stars with the most trustworthy radii, the ones where distance is known well and extinction is moderate, are generally not the ones with the largest quoted figures. This is not a scandal, it is science being science. The frontier of knowledge is always where the uncertainty is greatest, and in stellar astronomy the frontier of the size ranking is genuinely uncertain terrain. What matters is knowing that and holding the numbers accordingly. With that honesty in hand, settle in, because the next entries on the list are genuinely spectacular, even with their caveats, even knowing the numbers are approximate. The scale is real, even if the precise figures are not settled, and the stories attached to these stars are some of the most vivid in modern stellar astronomy. So let us begin with the star that currently sits at the top of most rankings, the one that if you search for the largest star right now, you will probably find named first. Stephenson 2-18, it is also the star that comes with the largest asterisk. Stephenson 2-18, sometimes written as ST218 or catalogued as RSGC218, is a red supergiant living inside a stellar cluster called Stephenson 2, out in the constellation Scutum, the same patch of sky that gave us UY Scuti. The cluster itself is a dense collection of evolved massive stars, relatively well studied, sitting roughly 6,000 light-years from us, deep in the galactic plane. And if Stephenson 218 genuinely belongs to that cluster, and if the cluster's distance is what astronomers think it is, then the numbers that follow are extraordinary, roughly 2,250 solar radii. That is the figure that appears most often in the literature, and it is the number that has pushed Stephenson 218 to the top of the size leaderboard. If true, it would make this star the largest known stellar object in the observable universe by a significant margin over everything else on this list. To put that in the terms we have been building throughout this evening, remember that one solar radius is about 696,000 kilometers. So 2,050 solar radii is a diameter of nearly 3 billion kilometers. If you placed Stephenson 2-18 at the center of our solar system, in the seat currently occupied by the Sun, its surface would not merely swallow the inner planets. It would reach past Jupiter, it would extend past Saturn, it would push out toward Uranus. You would need to travel somewhere in the neighborhood of Uranus's orbit, more than 2.5 billion kilometers from home, before you finally cleared the surface of this star. Let that rest for a moment. Not Jupiter, not Saturn, Uranus. That is what 2,050 solar radii actually means, translated into distances we can almost imagine. And now comes the asterisk. The entire calculation rests on a single assumption: that Stephenson 2-18 is actually a member of the Stephenson 2 cluster, sitting at the cluster's distance, embedded in its stellar family. If that assumption holds, then the size estimate flows from it in a fairly straightforward way. You know the distance? You measure the star's brightness and temperature, you run the physics, and you get a radius. But what if it doesn't hold? The Stephenson 2 cluster is embedded in the galactic plane, which is exactly the kind of region where projection effects play tricks on us. Stars that happen to lie in the same direction as a cluster, but are actually much closer or much farther away, can look from our vantage point like they belong to that cluster. They are along the same line of sight. They might even look similar in color or spectral type. But if one of them is a foreground object sitting perhaps 2,000 or 3,000 light-years closer to us than the cluster, then its true distance is much smaller, which means its true luminosity is much smaller, which means its true radius is much smaller. The number collapses. Astronomers working on the Stephenson 2 cluster have noted this ambiguity explicitly. Confirming true membership requires radial velocity measurements, checking whether the star is moving with the same velocity as the rest of the cluster in space. For Stephenson 218, those measurements are difficult to make with high precision, partly because the star's spectrum is complex, and partly because the cluster environment is crowded. The membership question has not been resolved to everyone's satisfaction, so there it sits, at the top of the ranking, wearing a crown that might be perfectly real, and might dissolve the moment better measurements arrive. It would not be the first time a record holder's number has been revised. We have already watched that happen with UY Scuti. We have watched it happen, to a lesser degree, with nearly every star that has briefly held the title. And we will keep watching it happen because that is how the science moves. What you can say about Stephenson 218 without any asterisk is this: it is almost certainly one of the largest stars known. Even in conservative scenarios that would reduce its quoted radius substantially, it is still an extraordinary object, a red supergiant in a late, unstable phase of its life, surrounded by other massive evolved stars in one of the richest clusters in the galaxy. The argument about the precise number does not change what it is, it only changes the superlative. And given everything we have discussed about how these numbers are made, you might find it reassuring rather than disappointing that astronomers are still arguing. The argument is the sign of careful work. Let us move now to the next entry, and in some ways the most honest example of the uncertainty problem in this entire ranking, Westerlund 126. The name tells you something about its home. Westerlund 1 is a superstar cluster, one of the most massive young stellar clusters in the Milky Way, lying in the constellation Ara the Altar, somewhere between 15 and 16,000 light-years from us. It was discovered by the Swedish astronomer Bengt Westerlund in 1961, and it is extraordinary territory. Westerlund 1 contains dozens of massive evolved stars, multiple yellow hypergiants, red supergiants, and the remains of stars that have already ended their lives, all packed into a region only a few light-years across. It is a window into what happens when a huge number of massive stars form together and evolve together, pushing each other through their lives. And in the middle of that cluster, or rather associated with it, sits Westerlund 126, designated WD 126, one of the largest and most luminous red supergiants, or hypergiants, yet identified. The radius estimates for WD 126 range from roughly 1,500 solar radii to 2,500 solar radii. Read that again slowly. 1,500 at the low end, 2,500 at the high end. That is not a small error bar. That is a range of 1,000 solar radii, which is itself 3 times the radius of our Sun expressed as a unit of comparison. The uncertainty on WD 126's size is, on its own, bigger than most of the stars on this list. Why so uncertain? The reasons will feel familiar by now because they are the same forces we have been tracing all evening. Westerlund 1 sits in the galactic plane, embedded in some of the dustiest, most crowded terrain in the Milky Way. The extinction, the absorption and reddening of light by intervening dust is severe. The distance to the cluster, while reasonably well constrained, carries its own uncertainties, and different studies using different methods have arrived at slightly different values. The star itself is difficult to observe cleanly in a cluster this dense, and WD 126 is a hypergiant, which means even its photosphere, the visible surface, is not a stable, well-defined structure. It breathes, it pulsates, it sheds material. Its outer layers are dynamically complex in ways that resist clean characterization. When you pile all of those factors together, the honest answer to the question of how big Westerlund 126 is becomes simply very large. Probably somewhere in the range of 1500 to 2500 solar radii, possibly near the top of that range, possibly nearer the bottom. The precision is genuinely not there yet. There is something quietly useful about including WD 126 in this list, not because of a dramatic story or a record number, but because it illustrates something important about how stellar astronomy actually works at the frontier. The most extreme objects are, by definition, the hardest to measure. They are rare, so there are few of them to compare against. They are often in dense, obscured environments because that is where the most massive stars form. Their own behavior, the pulsating, the mass shedding, the instability, blurs their edges, and the instruments we would need to pin them down precisely, high-resolution interferometers capable of resolving objects at distances of 15,000 light-years, are operating at the very edge of what current technology can achieve. So WD 126 is on this list as a reminder that the ranking is not a clean table of settled numbers. It is a collection of best current estimates, each one honest about the fact that it might change. And in the meantime, even at the conservative end of its range, Westerlund 126 is an object that would engulf most of the solar system if placed where the Sun is. What strikes you if you spend time with these numbers is a pattern. The stars that make the loudest claims, the ones at the top of the ranking with the most quoted figures, the ones that tend to appear in size comparison videos without any hedging, are almost always the ones with the most problematic measurements. The most dramatic sizes come from the most uncertain distances. The loudest headlines are attached to the thinnest certainty. And this invites a question that is actually the most interesting one on the list. If the Milky Way's headline champions are so hard to pin down, is there any star whose size we actually trust? Yes. And it lives in another galaxy. This is the counterintuitive thing. The most reliably measured giant stars are not the ones nearest to us, not the ones we can observe in the most detail, simply because of proximity. They are the ones that live in the Large Magellanic Cloud. Here is why. To calculate a star's radius from its luminosity and temperature, you need to know how far away it is. Closer is not automatically better, because if a star is buried in the galactic plane, as most of the Milky Way's extreme supergiants are, the light reaching us is distorted by thousands of light-years of intervening dust and gas. Disentangling the star's true brightness from the extinction it has suffered is itself a major source of error. The photometric measurement depends on a correction, and the correction carries its own uncertainty. For stars in the Large Magellanic Cloud, a companion galaxy to our Milky Way, the situation is different in a key way. The distance to the Large Magellanic Cloud is known remarkably well, anchored by multiple independent methods, including the precise timing of light echoes from the supernova SN 1987A, which exploded there in 1987, and by observations of eclipsing binary stars whose orbital mechanics give direct geometric distances. The current best value for the distance to the Large Magellanic Cloud is approximately 163,000 to 170,000 light-years. That number is trusted, and crucially, the Large Magellanic Cloud sits well outside the plane of our galaxy, in relatively clean space above the Milky Way's disk. The line of sight to LMC stars does not pass through the densest clouds of the galactic plane. The extinction, while not zero, is far more manageable, far better characterized. So when astronomers observe a star in the Large Magellanic Cloud, they know the distance to high confidence. They know the extinction to reasonable confidence. The radius they calculate carries much smaller systematic errors than the equivalent calculation for a Milky Way supergiant at the same apparent distance. This is the precise reason why, when you want a trustworthy number for a very large star, you look to the Magellanic Clouds. And in the Large Magellanic Cloud, the most famous and extraordinary example is WOH G64. WOH G64 is a red supergiant, or more precisely, a red hypergiant, one of the most luminous and physically largest stars known in the local group of galaxies. The name, WOH G64, comes from the catalogue designation assigned by the astronomers Westerlund, Olander, and Hayden in a survey of the Large Magellanic Cloud. It sits in the LMC at the distance we just discussed, roughly 163,000 light-years from us. Its radius is estimated at approximately 1,540 solar radii. Some papers cite figures ranging from roughly 1,500 to perhaps 2,000 solar radii, with the spread arising from different assumptions about its luminosity and temperature profile. But the important thing is that these estimates are built on a solid foundation. The distance is known, the extinction is constrained. The measurement is not perfect, no stellar radius measurement ever is, but it is far more robust than most of the Milky Way numbers that fill the top of the ranking. At 1,540 solar radii, WOH G64 would, if placed at the center of our solar system, extend its surface out past the orbit of Jupiter, deep into the space where the gas giants live. You would need to be somewhere between Jupiter and Saturn before the star's surface fell away behind you. That scale is not a record in the way Stephenson 218's contested 2,150 solar radii might be, but it is a real number attached to real physics anchored to a real known distance. In a ranking built on honest uncertainty, that gives WOH G64 a kind of credibility the other stars on this list cannot quite match. And then in 2024, something happened that made WOH G64 not just a trustworthy giant, but a genuinely historic one. For the first time in the history of astronomy, a detailed close-up image was captured of a star outside our galaxy. Think about what that sentence means. We have been looking at other galaxies for centuries. We have catalogued millions of stars in the Large Magellanic Cloud. Alone, we have measured their brightnesses, their temperatures, their chemical compositions through spectroscopy. But actually resolving a single star in another galaxy, actually seeing its disk, its structure, the space around it in fine detail, had never been done. The distances involved make it almost impossibly difficult. Even the largest stars, tens of millions of kilometers across, appear as point sources of light from tens of thousands of light-years away, let alone 163,000 light-years. The achievement required the gravity instrument. Gravity is an interferometric beam combiner installed at the Very Large Telescope in Chile, operated by the European Southern Observatory. What interferometry does is combine the light from multiple separate telescopes, in gravity's case the 4-unit telescopes of the Very Large Telescope Interferometer, separated by up to 130 meters, to effectively synthesize the resolving power of a single telescope 130 meters across. That allows astronomers to resolve angular structures far smaller than any individual telescope could see, reaching down into milliarc-second or even sub-milliarc-second scales. WOH G64 is large enough and, within the context of the Large Magellanic Cloud, close enough that with gravity's capabilities the team could resolve actual structure around it. What they found was extraordinary. The image revealed a dust cocoon around WOH G64, but not a spherical cocoon, the way you might imagine a symmetrical shell of material puffed outward in all directions. What the gravity observation revealed was an egg-shaped structure. An elongated, oblate dust envelope wrapped around the star. The dust is the star's own material, shed from its outer layers as it ages and expands and destabilizes, cast off into the surrounding space and catching the star's radiation, glowing by reflected and re-emitted light. An egg-shaped cocoon around a dying star, 63,000 light-years away, imaged for the first time. Let that settle in for a moment. This is not an artist's rendering based on spectroscopic data or model inferences. This is an actual resolved image of the immediate environment of a star in another galaxy. The asymmetry of the cocoon tells astronomers something important too. A perfectly spherical shell of ejected material would suggest the star is losing mass more or less uniformly in all directions. An egg-shaped, elongated envelope suggests that the mass loss is not isotropic, that there is more material in some directions than others. This could reflect the star's rotation, or the influence of a companion, or complex dynamics in the stellar envelope driven by convective motions. The physics of what drives asymmetric mass loss in massive evolved stars is still an open research question, and the WOH G64 image feeds directly into that conversation. But for our purposes here, for the story we are building on this quiet night, there is something more immediate in that image. It shows a star actively dying. WOH G64 is shedding its outer layers. The cocoon around it is made of material that was once part of the star, that has drifted away from the surface and is now surrounding it like a shroud. The star is in a phase of its life where it is losing mass at a significant rate, building up that cloud of dust and gas around itself as it ages. At some point in the future, not tomorrow, not in 10,000 years in any meaningful human sense, but at some point in astronomical time, that process will end in a violent, catastrophic conclusion, a supernova or perhaps a hypernova. The energy of an exploding star released in seconds, brighter than entire galaxies for a brief time. That dust cocoon is the evidence. The star is falling apart slowly, gently, compared to the explosion that will eventually finish it, but inexorably. And in 2024, for the first time, we had a picture of it happening. What makes WOH G64 sit so comfortably on this list is that its story weaves together several threads we have been following all evening. It is a real, trustworthy radius, not a contested estimate hinging on a fragile assumption. It is in a location, the Large Magellanic Cloud, whose distance we actually know well. It is a star we can actually talk about with some confidence. And then on top of that foundation of honest measurement comes something genuinely new, an image that has never existed before of a process that has been underway for millions of years. In a ranking that is full of caveats, WOH G64 is the one that earns its place most cleanly, and it is doing something that every other star on this list is also doing, to varying degrees in its own way. It is losing mass, shedding material, pushing its own substance out into the surrounding space. This is not incidental. It is the point. Every star on this list is a red supergiant or red hypergiant, a massive evolved star in the late phases of its life. The enormous size is not something they started with. When these stars were young, on what astronomers call the main sequence, burning hydrogen in their cores, they were hot and blue and compact, not much larger than the solar radii range that massive young stars occupy. The swelling to hundreds or thousands of solar radii came later as the core composition changed, as the nuclear burning shell moved outward, as the outer envelope expanded in response to the changes happening in the deep interior. In other words, the enormity is a symptom. An enormous red supergiant is not a star at the peak of its power. It is a star in the process of ending. The size is the sign of a system out of equilibrium, a star whose outer layers have inflated far beyond the compact configuration of its youth, a star that is in some sense falling apart in slow motion, even before any final explosion. And the falling apart is, in many cases, literal. Not just the nuclear evolution of the interior, but the actual physical shedding of mass. Red supergiants lose material to stellar winds, to convective upheavals that send giant plumes of gas rising from the interior to the surface, and then beyond, to episodic eruptions that eject concentrated blobs of material in specific directions, like the tendrils imaged by the Hubble Space Telescope around VY Canis Majoris, or the dust cloud from an ejection event that caused Betelgeuse's great dimming in 2019 and 2020. These are not metaphors, they are documented, imaged, measured events. Stars of this kind actively reduce themselves over time, losing solar masses of material across their lives. This matters for the ranking in a subtle but important way. A star's measured size at any given moment is just that, a moment. A snapshot of a pulsating, variable, dynamic object whose radius can change by significant amounts over months or years. The radius of a red supergiant is not a fixed property the way the radius of a rock is a fixed property. It breathes, it swells and contracts on timescales ranging from months to decades. UY Scuti is known to be a variable star, its brightness changing over a period of roughly 740 days. Betelgeuse varies semi-regularly. WOH Canis Majoris is irregular and turbulent. When you measure one of these stars and report a radius, you are reporting the radius at a particular phase of a complex pulsation cycle, with the understanding that the star was somewhat larger yesterday and will be somewhat smaller tomorrow, or the reverse. This too is part of the honest picture. The ranked list of the 7 largest stars is not a stable table of permanent records. It is a photograph taken now of objects that are changing using measurements that carry systematic uncertainties built on distance assumptions that might themselves be revised. The list is our best current understanding. It is not a final answer. But here is the thing, even knowing all of that, even holding all of those caveats comfortably in mind, the scale involved is genuinely staggering. We are talking about objects that would engulf the inner solar system, objects that, if dropped where the sun sits, would make the sun's familiar neighborhood, the space where Earth orbits, the space we call home, entirely interior to another star. That fact is not provisional. That fact does not change with better parallax measurements. Even if Stephenson 2-18 turns out to be half as large as currently estimated, it is still an object of inconceivable scale. Even if every star on this list shrank by 30% tomorrow due to improved Gaia data, they would still be among the most extreme physical structures in the observable universe. The honesty about uncertainty is not an argument for dismissing the scale. It is an argument for holding the scale with the same care the astronomers who measure these things try to hold it. And as we move toward the deepest part of this evening's journey, toward the physics that underlies everything we have been discussing, it is worth pausing on WOH G64 one more time, because that egg-shaped cocoon, that shroud of shed material, is not just a beautiful image. It is evidence of a process that connects directly to why these stars are as large as they are, and why none of them can be much larger. The mass loss is not random. It is not simply gravity failing. There is a physics to it, a driving force. And to understand that force, you need to understand something about what is happening deep inside these enormous, bloated, dying stars. We have touched on this briefly, but now we need to go deeper into it. Because the cocoon around WOH G64 and the tendrils around WOH Canis Majoris and the dimming events of RW Cephei and Betelgeuse are all manifestations of the same underlying physics, and that physics is the story of why there is a ceiling, why you cannot simply keep building bigger and bigger stars indefinitely, why the giants we have been discussing tonight are not just the largest known but are approaching the largest possible. The answer has to do with light, with the fact that light, for all its ethereal quality, for all that it passes through glass and reflects off mirrors and carries no weight you could ever feel, does exert a force, a pressure. When a photon, a particle of light, travels through space and strikes an atom or an electron, it transfers a tiny amount of momentum. The atom recoils slightly. For any individual photon, for any individual atom, this effect is utterly negligible. You will never feel the pressure of sunlight on your skin, not in any mechanical sense. But inside a star, where the energy being produced in the core is unimaginably large, and where that energy must make its way outward through the stellar interior, the cumulative pressure of billions upon billions upon billions of photons streaming outward is not negligible at all. This outward pressure of radiation is always present in stars, always pushing matter outward, always competing with the inward pull of gravity, always in tension. In most stars, gravity wins comfortably. The pressure of radiation is a minor player, a small perturbation in the much larger contest between gravity and the pressure of hot gas. The Sun is in this regime. Its radiation pressure is present but far from dominant. But as stars become more massive, as they burn fuel at higher rates and generate far more luminosity, the radiation pressure grows, and the key insight, the thing that Sir Arthur Eddington worked out, is that the radiation pressure scales differently with mass than the gravitational pull does. As a star gets more and more massive, its luminosity rises steeply, much faster than its mass does. A star twice as massive as the Sun is not twice as luminous. It is many times more luminous. Luminosity scales with mass in a power law that is steep enough that at very high masses, the radiation pressure eventually starts to catch up with gravity, and at a certain point, it catches up completely. At that point, the outward push of radiation exactly balances the inward pull of gravity on the outermost layers of the star. This is the Eddington limit, named for Sir Arthur Eddington, the British astrophysicist who first derived it in the early 20th century. It is sometimes called the Eddington luminosity, and it represents a kind of physical wall. A star that reaches its own Eddington limit is in a precarious situation. The radiation pressure from the interior is strong enough to match gravity at the surface. If the luminosity increases further, even slightly, the radiation pressure exceeds gravity, and the outer layers of the star are no longer gravitationally bound. They start to be pushed away. The star begins to shed mass, not through a gentle stellar wind or a slow evaporation, but through a direct radiative driving. The star's own light is blowing itself apart. And here is the crucial connection. As the star sheds mass, it loses luminosity, which reduces the radiation pressure, which allows gravity to reassert control, which slows the mass loss. This is the self-regulating mechanism. A star approaching the Eddington limit does not simply explode instantly. It enters a regime of instability, of violent mass loss, of eruptions and ejections, where it is constantly teetering near the wall, shedding enough material to stay just barely below the limit, never able to cross it permanently without tearing itself apart. This is why the most massive stars we observe, the ones that sit closest to the theoretical upper mass limit, are not calm and stable objects. They are among the most violent and variable stars in the sky. They erupt, they pulsate, they shed enormous quantities of material. They are fighting constantly against a physical ceiling. And this is the explanation for why Westerlund 126's dimming event and R.W. Cephei's dimming event and Betelgeuse's great dimming are not random bad luck or coincidence. They are all instances of the same underlying instability, different expressions of stars that are large enough, luminous enough, close enough to their own physical limits to be prone to exactly these kinds of violent mass-shedding episodes. The cocoon around WOH G64 is the same story told in dust. A star that has shed so much of itself that it is now wrapped in the debris of its own shedding. A dying giant surrounded by the evidence of its own long, slow dissolution. And all of this, the mass loss, the instability, the shedding of material, the Eddington limit, circles back to the question the title of this evening's exploration promised to answer. Not just what the largest stars are, but why none of them can be much larger, why the list stops where it stops, why the giants on this ranking are near a ceiling, not in an open field with plenty of room above them. To fully understand that ceiling, we need to hold together two things that this part of the evening has been quietly assembling. First, the distinction between being large and being massive. Second, the mechanism by which the Eddington limit acts on both. The stars on our size ranking, Stephenson 2 to 18, WOH G64, UY Scuti, VY Canis Majoris, the others, are red supergiants and red hypergiants. They are cool stars, cool in the stellar sense, with surface temperatures of roughly 3000 to 4000 Kelvin, glowing red and orange rather than blue and white. They are physically enormous, with radii ranging from hundreds to over 1,000 times the Sun's. But for all their enormous size, they are not the most massive stars. Their size is a consequence of inflation, of the outer envelope swelling as the stellar interior evolves, not a consequence of containing the most matter. A red supergiant of 1/500 solar radii might contain somewhere in the range of 10 to 30 solar masses. Perhaps more, perhaps a little less, but not hundreds of solar masses. The stars that contain hundreds of solar masses look nothing like the stars on this list. They are hot and blue, compact. Their radii are measured in tens of solar radii, not thousands. They burn their fuel at such ferocious rates that they pour out energy at luminosities 1,000,000 times or more the Sun's, and it is precisely that ferocious luminosity that places them so close to the Eddington limit. They are not blowing up because they are fragile. They are blowing up because they are so powerful that their own light is strong enough to push matter off their surfaces. These two families of stars, the cool, bloated, enormous red hypergiants and the hot, compact, ferociously luminous blue hypergiants and Wolf-Rayet stars, are both near their respective limits. But they are near different aspects of the same underlying physics. The cool red giants are near their limits in a structural sense. The inflation of the outer envelope has proceeded so far that the outer layers are only loosely bound, with surface gravities much lower than a main sequence star of the same mass. The pulsations and convective upwellings can drive mass loss even without pushing against the full Eddington limit, simply because the material in the outer layers is held so gently. The hot blue massive stars are near the Eddington limit in the luminosity sense. Their radiation pressure is so strong relative to gravity that the limit is approached directly through radiative driving, and above the Eddington limit, stars cannot persist stably. They shed mass until they come back below it. The limit is not merely a theoretical boundary, it is a regulator, a governor that the universe imposes on stellar masses. This is why there is a ceiling. Not just that we haven't found anything bigger yet, but that there is a physics reason, a mechanism, a law that prevents stars from growing past a certain point and staying there. The Eddington limit is the wall the title promised. And on the other side of it, the stars do not simply get bigger, they begin to self-destruct. There are rare stars, documented and studied, that appear to have crossed or approached the Eddington limit in dramatic fashion. And of all of them, none makes the physics more vivid, more visible, more impossible to ignore than the one we will turn to next. A star in our own galaxy, not in the record books for size or mass, but for something else entirely. For what it did one morning in the 1840s when it briefly blazed so brightly it became the second brightest star in the entire sky, and in doing so demonstrated exactly what happens when a star presses too hard against the wall. But before we arrive at that spectacular moment, in the galactic neighborhood of Eta Carinae, and the full drama of the Eddington limit made visible, there is one more star on the countdown that we need to meet. A star in our own Milky Way, in the constellation Canis Major, surrounded by a nebula of its own making, caught by the Hubble Space Telescope in the act of shedding great arcs and knots and tendrils of material into the space around it. A star that, in the most literal visual sense, is coming apart. A star that makes the tearing itself apart theme not a metaphor, but an image you can look at directly. Its name is WOH Canis Majoris, and WOH Canis Majoris is something else. There is something different about seeing it, rather than just being told the number. Most of the stars we have talked about tonight exist, for us, as measurements, as figures derived from angular diameters measured in milliarc seconds, from luminosity curves and temperature spectra, from the careful mathematics of interferometry. They are real, they are enormous, but they live, mostly, in the language of astronomy rather than in images we can hold in the mind. WOH Canis Majoris is different. The Hubble Space Telescope has looked at it, and what Hubble saw was not a clean, well-behaved star sitting serenely in space. What it saw was a star surrounded by a sprawling, chaotic, beautiful mess of its own making. Arcs of gas and dust, knots of ejected material, tendrils streaming outward, great loops and filaments of matter that were once part of the star itself, flung off into the surrounding space over thousands of years of violent, irregular shedding. The star has been building its own nebula piece by piece, eruption by eruption, and Hubble caught it mid-construction. So when we say that the giants on this list are stars in the process of coming apart, WOH Canis Majoris is the one you can actually see doing it. It sits in the constellation Canis Major, the Great Dog, which most of you in the Northern Hemisphere know because it contains Sirius, the brightest star in the night sky. WOH Canis Majoris is nowhere near as visually prominent as Sirius. It is red and variable and deeply embedded in the dusty, crowded neighborhood of the galactic plane. But in terms of raw physical scale, it is extraordinary. The older measurements of WOH Canis Majoris were, as we have come to expect by now, very large. Some early estimates put it at around 1/800 to 2100 solar radii. For a while it held the title that UY Scuti later claimed, the largest known star, and it carried that distinction in textbooks and popular accounts for years. Then better data arrived, as it always does, and the number came down. The modern estimate for WOH Canis Majoris sits at around 1,120 solar radii. Still enormous. Still a star that, placed at the center of our own solar system, would swallow Mercury, Venus, Earth, Mars, most of the asteroid belt, and reach out to encompass Jupiter entirely. The surface of WOH Canis Majoris would be somewhere in the middle of the space we normally think of as the solar system's inner neighborhood, but a number, even a vivid one, only goes so far. What makes WOH Canis Majoris remarkable is not just the scale, but the behavior. Red hypergiants of this class are not stable, quiet objects. They are in a late and turbulent phase of stellar evolution, bloated far beyond what gravity can hold comfortably, their outer layers loosely bound, their surfaces churning and variable. And WOH Canis Majoris is one of the most dramatic examples we know of a star in exactly this condition. Its brightness changes irregularly, its surface pulsates, and periodically, over timescales of centuries, it sheds enormous quantities of material in asymmetric eruptions that produce exactly the structures Hubble later imaged. Those arcs and knots and tendrils are not decorative. They are the material cost of instability. They are the star throwing parts of itself away. The technical term for this kind of behavior is mass loss, and all massive evolved stars do it. But WOH Canis Majoris does it conspicuously and continuously, at a rate that has produced a surrounding nebula complex enough to map in detail. Each feature in that nebula corresponds to a different episode of mass ejection at different times, in different directions, with different velocities. It is, in a sense, a history of the star's recent life written in the surrounding gas and dust. And then there is what comes next for it. WOH Canis Majoris is not going to drift quietly into a stellar retirement. Stars of this mass do not get to do that. When a red hypergiant of this size and mass reaches the end of its available fuel, it collapses and explodes, It becomes a supernova, or in some cases, given enough mass and the right conditions, something more energetic still, what astronomers sometimes call a hypernova. VY Canis Majoris is considered a strong supernova candidate. We do not know exactly when this will happen. It could be in 10,000 years or 100,000 years, which on a human scale is an eternity, but on a cosmic scale is barely a breath. The star is in the final chapter. The mass loss it has been doing with such enthusiasm is partly that chapter being read aloud. What is interesting in the context of everything we have been building toward tonight is that this behavior, this active shedding of mass, is not incidental to a star's size. It is connected to it. The most luminous, most massive stars are the ones most aggressively pressed against the physical limits we are about to discuss. And the shedding of mass is, in part, the mechanism by which those limits are expressed. The wall does not just stop stars from growing bigger, it makes the largest ones bleed. So let us take a breath here, because we have now moved through all 7 of our principal giants. We have walked through the measurement controversies and the distance problems and the fuzzy, ill-defined surfaces and the dimming events and the dying star in the Magellanic Cloud imaged in unprecedented close-up. And woven through all of it has been a theme that every single one of these stars shares. Every one of them is enormous, not because it is powerful and stable, but because it is evolved and destabilized. Every one of them is shedding mass. Every one of them is in the last chapters of a life that was always going to be brief and violent. And now we have arrived at the question the title actually promised to answer. Not which star is biggest, but why none can get much bigger. Because there is a wall. A real, physical, mathematically precise wall. And to understand it, we need to take a small detour to talk about 2 stars that are not on the size list at all, but which illuminate the mechanism more clearly than anything else we have discussed. The first is R136A1, the most massive star reliably known. The second is Eta Carinae, a star that has dramatically demonstrated what happens when you press too hard against the wall. And at the center of both stories is a physicist named Arthur Eddington and a limit that bears his name. Let us start with R136A1. It lives in the Tarantula Nebula, one of the most spectacular star-forming regions in the nearby universe. The Tarantula Nebula sits in the large Magellanic Cloud, the same small satellite galaxy that holds WOH G64. And like WOH G64, the stars in it benefit from the large Magellanic Cloud's well-established distance of around 163,000 light-years. At the heart of the Tarantula Nebula is a cluster of extraordinarily massive young hot stars called R136. And at the center of R136 is R136A1, a star so massive it sits at or beyond the theoretical upper limit of what a star is supposed to be able to be. For many years it was cited as having a mass of somewhere around 265 to 315 times the mass of our Sun. That number made it not just the heaviest star known, but a star that seemed to challenge the models, a star that appeared to exceed the theoretical upper mass limit that stellar physics predicts. And then in 2022, a new study using the Gemini Observatory's Zorro Speckle Imager, a high-resolution imaging instrument, produced sharper data on the R136 cluster and revised R136A1's mass downward. The new estimate came out at around 196 solar masses. Still phenomenal, still the most massive star reliably known, but lighter than previously thought. And this again is the pattern we have seen all night. The record holders keep being revised, not because the stars change, but because our measurements do. R136A1 did the same thing that UY Scuti did, that Stephenson 218 may yet do, that Westerlund 126 already showed us in the range of its own estimates. The number came down when the data improved, But here is where R136a1 becomes a different kind of important to this story. Look at its size. R136a1, despite holding around 196 times the mass of our Sun, or even 265 times the mass of our Sun, in the older estimate, has a radius of only a few tens of solar radii, maybe 30 or 40, possibly a little more or less, depending on the model and the measurement, but the order of magnitude is clear. It is a star with roughly tens of times the Sun's width. It is, by the standards of everything we have discussed tonight, compact. Think about that for a moment. Hold Stephenson 218 in one hand, a star with perhaps 2,150 solar radii, a sphere whose surface would reach past Saturn, and hold R136a1 in the other, a star holding close to 200 times the Sun's mass, a gravitational engine of almost incomprehensible power. And then notice that R136a1, the heavier one, is perhaps 50 times smaller in radius than the lighter one. Largest and most massive are not the same list. They are not even the same type of object. They come from different physical regimes entirely. UY Scuti and Stephenson 218 and WOH G64 and VY Canis Majoris are red supergiants and red hypergiants. Cool stars. Their surface temperatures hover around 3,000 to 4,000 degrees Kelvin. They are enormous because their outer envelopes have expanded and cooled enormously, spread thin over a volume of space that strains the imagination. But they do not hold great mass. They are not the heaviest objects. A star can be enormous in radius while being relatively modest in mass, because mass is measured by how much material is there, and radius is measured by how far the outermost layers reach. And those two things can behave very differently depending on the conditions inside the star. R136a1 is something else entirely. It is hot, blue-white, a Wolf-Rayet type object in the regime of luminous blue variables, ferociously luminous, pouring out energy at a rate that dwarfs anything the red giants can manage. It is compact not because it has less material, but because the high temperature keeps its outer layers from puffing outward in the same way. The pressure and radiation coming from inside push outward, yes, but the star is also losing mass violently through stellar winds, these fierce outflows driven by radiation pressure, and this continuous mass loss keeps it from ever having a chance to inflate into a red supergiant. It burns hard and hot and fast, shedding mass all the while, and it stays compact. And this is where Arthur Eddington comes in. Sir Arthur Eddington was a British astrophysicist who worked in the early decades of the 20th century. Among his many contributions to science, he worked out a fundamental relationship in stellar physics, one that turns out to have enormous consequences for how big and how massive a star can be. The idea is this: a star is a balance. On one side you have gravity, pulling all the star's material inward toward its center. On the other side, you have pressure pushing outward, the pressure from the hot gas inside and, crucially, from radiation itself. Light carries momentum. When a photon of light collides with a particle, it pushes that particle. In everyday life, the effect is imperceptibly small. But in the interior of a star, where the density of light is unimaginably high, radiation pressure becomes a real physical force. For most stars, including our Sun, the radiation pressure contribution is small compared to the gas pressure. But as a star becomes more massive, its core has to burn faster and hotter to support itself against the greater weight of material pressing down. A more massive star is brighter, much brighter. And in stellar physics, brighter very rapidly means far brighter, because luminosity does not scale slowly with mass, it scales steeply, dramatically. A star twice as massive as the Sun is not twice as luminous, it is many times more luminous. The luminosity of massive stars rockets upward with mass far faster than mass itself increases. And if luminosity keeps climbing, so does radiation pressure. At some point, if you keep adding mass to a star and making it more luminous, the radiation pressure pushing outward on the star's outer layers grows until it equals the gravitational pull holding those layers in place. And then if you push further, the radiation exceeds gravity and the star cannot hold on to its outer material. The light literally pushes the outer layers off the star. This is the Eddington limit, named for Sir Arthur Eddington. The luminosity at which the outward pressure of a star's own light exactly balances the inward pull of its gravity. Beyond the Eddington limit, a star cannot remain stable. It sheds mass. Violently, continuously, or in great episodic eruptions, it pushes material off itself to bring its luminosity back down to something it can sustain. The wall does not stop stars from existing above it. It stops them from staying there. Stars that approach the Eddington limit bleed, and by bleeding, they stay closer to the boundary of what is survivable. This is why there is a practical upper mass limit for stars. Because mass makes luminosity, and luminosity runs up against the Eddington limit, and beyond a certain mass, a star loses material faster than it can accrete it. It sheds what makes it too heavy. The theoretical upper mass limit derived from Eddington-type arguments and from the statistics of stellar populations in dense clusters sits at around 150 solar masses, and yet R136a1 appears to exceed it at 196 solar masses even after revision, and this is thought to be because stars in extremely dense cluster cores can merge with other massive stars, combining their masses in a way that briefly pushes above the typical limit. The upper mass limit is real, but the extreme environment of a cluster like R136 can bend the rules slightly for a short time. What this means for the size list for our 7 giants is this. The stars that can grow the largest in radius are specifically the ones that have evolved away from the hot, massive regime. The red supergiants and red hypergiants are cool and bloated because they are evolved late-phase objects that have already burned through much of their fuel. They do not have the intense radiation pressure of a hot, compact blue star, and precisely because they lack that pressure, they can expand enormously without immediately blowing themselves apart. The cool envelope can puff outward to 1,000 or 2,000 solar radii without crossing the Eddington limit, in the same way a hot, luminous star would. But they are not immune. Even these cool giants lose mass. Even they have their version of the bleeding. The mass loss from red supergiants and hypergiants is slower and less dramatic than the wind-driven shedding of a hot blue star, but it is real and continuous, and in some cases, as VY Canis Majoris shows us, it is punctuated by great asymmetric eruptions. So the 2 lists, the largest and the most massive, stop at the same wall. They just approach it from different directions. The hot, compact, massive stars like R136a1 are held near the wall because radiation pressure prevents them from getting much heavier without blowing themselves apart. The cool, expanded, enormous stars like UY Scuti or WOH G64 are near the wall in a different sense, losing mass and approaching the end of the conditions that allow them to be so large. Every star on our list tonight, in one way or another, is pressed against a limit, and then there is Eta Carinae. If you want to see what happens when a star runs hard into the Eddington wall and the wall wins, at least temporarily, Eta Carinae is the most spectacular documented example. It sits in our own Milky Way in the southern sky, roughly 7,500 light-years away. It is not on our size list. Its radius is not in the same range as the red hypergiants, but in terms of mass and luminosity, it is in another category entirely. Eta Carinae is a binary system, but the primary component is one of the most massive and luminous stars known in our galaxy, a luminous blue variable sitting, at least at some points in its history, extraordinarily close to the Eddington limit. And in the 1840s, something happened. We call it the Great Eruption. In 1837, Eta Carinae was already notable among astronomers as a bright star in the southern sky. But then it began to brighten. Through the 1840s, it climbed in luminosity until, In 1843, it briefly became the second brightest star in the entire night sky, outshone only by Sirius. This from a star that in normal times is not even comfortably visible to the naked eye without darkness and a southern horizon. To flare up to that brightness was extraordinary, astonishing, and the cause was the Eddington limit in action. What had happened was that Eta Carinae had undergone a giant stellar eruption. The star had pushed against its own radiation limit so hard that it began ejecting enormous quantities of material outward into space. Over the course of the Great Eruption and its subsequent activity, Eta Carinae is estimated to have expelled more than 10 solar masses of material, 10 times the entire mass of our Sun, thrown off into the surrounding space in a spectacular and relatively rapid outburst. The ejected material did not disappear. It formed a nebula around the star, which we can see today and which is called the Homunculus Nebula, from the Latin for little man, named for its distinctive hourglass or double-lobed shape visible in images. The Homunculus Nebula is, in effect, the solidified evidence of the Great Eruption. It is the material Eta Carinae threw off when it ran too hard into the wall and the wall pushed back. What makes this so important to the story we have been telling tonight is that the Great Eruption was not a supernova. Eta Carinae survived it. The star is still there. It is still luminous and still volatile and still monitored closely by astronomers, because a star that did what it did in the 1840s is a star capable of further dramatic behavior. In fact, there was a lesser eruption in the 1890s and the star continues to be active and variable. Eta Carinae is considered a prime candidate for a future supernova or hypernova, perhaps one that could produce a gamma-ray burst pointed in our direction, though the probability and timing are deeply uncertain, and the distance of 7,500 light-years puts us well outside the danger zone. But the Great Eruption stands as the most vivid, most human-scale, most documented example of what the Eddington limit looks like when it becomes an event rather than an equation. The star got too bright, the radiation pressure exceeded what the star could hold together, and the outer layers came off in a catastrophic outburst that briefly lit up the sky of the 1840s. People in the southern hemisphere looked up and saw a star that had not been so bright the week before, and brighter still the week after that, and they had no idea they were watching a star's outer atmosphere being physically blown away by its own light. The physics is straightforward in retrospect. The star approached the Eddington luminosity. At that luminosity, the outward pressure of radiation on the material in the star's outer layers exceeded gravity's inward pull. The material was accelerated outward. The eruption released energy at an extraordinary rate, making the star temporarily appear far more luminous than its equilibrium state. And then, having shed enough mass to pull its luminosity back below the critical threshold, the star settled again, battered and changed, but intact. That is the wall. That is what happens near it. And here is the beautiful, slightly humbling thing about all of this. Every star you have heard about tonight, every one of the 7 giants we have walked through, and every other massive evolved star in the galaxy is playing out some version of this same drama. The red supergiants puff outward and lose mass slowly. The hypergiants shed material in great irregular outbursts. The luminous blue variables like Eta Carinae erupt dramatically against the radiation limit. The Wolf Riot stars drive fierce stellar winds driven by radiation pressure, thinning themselves down as they go. All of them are bleeding. All of them are massive enough that the radiation produced inside them presses against the conditions that allow them to exist in their current form. Hugeness in a star is not permanence. It is a phase. And it is, in most cases, a final one. There is one more thread we should follow before we begin to wind down, and it is a theoretical one. So hold it lightly as a possibility rather than a measured fact. because it belongs to a category of science that is deeply informed and deeply considered, but which describes objects we have never actually seen. In the very early universe, shortly after the Big Bang, the first generation of stars to form would have been composed of a very different material than stars today. The universe had not yet produced significant quantities of anything heavier than hydrogen, helium, and traces of lithium. There was no carbon, no oxygen, no iron, no silicon. None of the heavier elements that astronomers call metals. Every element heavier than helium on the periodic table was either made inside a star or in a stellar explosion, and the first generation of stars, which we call population 3 stars, formed before any of that had happened. The absence of metals turns out to matter quite a lot for how stars form and how big they can get. One of the things heavy elements do in a contracting gas cloud is help it cool down efficiently through various radiation processes. A cloud that cools efficiently can fragment more readily, breaking into many smaller clumps that each form a smaller star. A cloud with no metals to facilitate that cooling process is less able to fragment. The contracting mass tends to stay together longer and fall into fewer, larger pieces. Theoretical models suggest that population 3 stars may have been able to grow to masses far larger than anything we see today, possibly hundreds of solar masses, possibly more. The conditions in the early universe before stars had seeded it with heavier elements may have allowed stellar masses that modern stellar physics would find impossible to sustain for long under today's conditions. But we have never seen a population star. They burned so fast and so hot, and the universe has had so much time to evolve since then that none of them could possibly survive to the present day. Their lifetimes were measured in millions of years, not billions, and they have long since exploded and seeded the early universe with the first generation of heavier elements. Every star we can observe today is a later generation, swimming in a universe already enriched by those earliest predecessors. So when we say the mass ceiling may have been higher in the early universe, we are saying something real and well motivated, but we are saying it about objects we can never directly observe. The stellar upper mass limit of around 150 solar masses that applies to the stars we can study today may not have applied then. The wall may have been placed differently or further away, but we are left reading the clues they left behind rather than the stars themselves. There is something quietly moving about that. The stars that may have been the most massive in all of cosmic history, the stars that in a strict physical sense might have been the closest thing the universe ever produced to objects truly bigger than anything we can observe now, are precisely the ones we cannot see. We know them only by what they left behind in the elements dissolved into every star and planet and person in the universe today, including us. And this, gently, is where we have been heading all along. We have spent this night moving from number to number, from measurement to measurement, from the contested 2050 solar radii of Stephenson 2-18 to the carefully anchored 1040 of WOH G64, from the revised and slightly humbled UY Scuti to the spectacular self-destruction of VY Canis Majoris, from the compact mass king R136A1 to the wall of light that Eta Carinae ran into one morning in the 1840s and made the whole southern sky briefly remember. And all of it, every single figure and every dimming event and every cloud of ejected gas imaged by Hubble and every milliarc-second measurement made by the VLTI and gravity instruments, all of it has been describing the same thing: stars in the process of dying, stars enormous precisely because they are in their final evolutionary chapters, bloated and unstable, shedding material back into the space they came from. The hugeness is not a sign of strength, it is a sign of completion. These stars have burned through what they were given, and in their last phase they have expanded to fill the sky around them, magnificent and temporary, and returning to the interstellar medium the elements they spent their lives forging. The carbon in your body was made in a star. The oxygen you are breathing right now was made in a star. The calcium in your bones, the iron in your blood, the silicon in the screen you might be glancing at tonight, all of it was cooked in the interior of a massive evolving star and scattered back into space when that star ended. You are, in the most literal chemical sense, made of the ashes of giants. Not the particular giants we have discussed tonight, because those are still alive, still burning, still shedding material and pressing against their limits, but their predecessors. Stars that came before that went through this same bloated, turbulent final phase and then released everything they had made. The calcium in your bones passed through the interior of a dying red supergiant. The iron in your blood was forged in conditions not so different from those inside VY Canis Majoris or WOH G64 before those stars themselves ever existed. You are here because stars like these ended. And when the giants on tonight's list do end, perhaps in tens of thousands of years or hundreds of thousands or a few million, they will add their contribution to the same slow cycling. The material of WOH G64 already being shed in that egg-shaped cocoon of dust and gas imaged by the gravity instrument in 2024 will drift through the large Magellanic Cloud and eventually, over vast timescales, become part of new gas clouds and new stars and possibly new planets. The tendrils imaged around VY Canis Majoris by Hubble are not waste. They are the early stages of that return. And when you look up at Cephei, Herschel's garnet star, deep red in the constellation Cepheus, you are looking at a star whose eventual supernova will scatter newly forged atoms across that part of the Milky Way. A star William Herschel noted and named for its color more than 2 centuries ago is preparing on its own time scale to enrich the galaxy. The question we started with tonight was a simple one. What is the biggest star? And the answer we have arrived at is layered and honest. We have an answer, or rather a set of candidate answers, with Stephenson 2 to 18 at perhaps 2,150 solar radii currently leading the nominal rankings, with WOH G64 offering a more trustworthy figure of around 1,040 solar radii because its distance is well established, and with UY Scuti and VY Canis Majoris and RW Cephei and Westerlund 126 and Cephei all clustered in the conversation, all carrying their measurement uncertainties and their distance assumptions and their contested cluster memberships and their ongoing revisions. The ranking is not settled, the individual figures are not precise. The surface of each of these stars is not a cleanly defined edge but a fuzzy, pulsating boundary that looks different depending on which definition you apply. The Rosalind radius and the optical depth surface and the dust formation boundary all give you different answers for the same star. Even the question itself, how big is it, turns out to require you to specify what you mean by big before you can begin to answer. But underneath the honest uncertainty, the answer to the title's second promise is clean and solid. Why can none of them get much bigger? Because of the Eddington limit, because the luminosity of a star scales steeply with its mass, and beyond a certain luminosity the star's own radiation pressure begins to overcome its gravity, and the outer layers are pushed away. The wall is not a matter of failing to find a bigger star, it is a matter of physics. A star that exceeds the Eddington luminosity sheds mass until it no longer does. The wall is self-enforcing, and this is why the largest stars by radius are never the most massive stars. The size champions are cool, bloated, evolved objects whose low temperatures allow enormous expansion without the catastrophic radiation pressure that comes with the hot blue giants. The mass champion, R136A1, barely a few tens of solar radii wide, would fit inside Stephenson 218 tens of thousands of times over in volume, and yet it carries around 196 times the mass of the Sun. Two different extremes, two different physical stories, both running up against the same fundamental ceiling from different sides. The biggest star is whichever one is currently winning the measurement contest, and that answer has changed before, and will change again as Gaia's parallax data continues to improve and as interferometric instruments reach further and sharper. The honest answer to which star is largest is probably still Stephenson 218 if its distance is what the cluster membership implies, but the honest qualifier is that we genuinely do not know its distance well enough to be certain, and the number may yet fall the way UY Scutis fell from 1/708 solar radii down toward 750 to 1000, not because the star moved, but because we finally measured it better. That is not a failure of science, it is science doing exactly what it is supposed to do, getting closer to what is true. And there is something restful about that, lying wherever you are right now, in the dark or in the soft glow of a lamp still on. The uncertainty is not a hole in the knowledge, it is the edge of it. The living edge where measurements are being improved and models are being refined, and the picture is still forming. WOH G64 showed us in 2024 that even a star in another galaxy can suddenly become more legible, that a new instrument can produce a first detailed close-up of something 163,000 light-years away, and reveal it to be a dying giant wrapped in its own shed skin, an egg-shaped cocoon of departing material. The knowledge is not finished. It is still arriving. The giants are still out there, in Scutum and Cepheus, and Canis Major, and the Stephenson 2 cluster, and the large Magellanic Cloud, doing what they have always been doing, which is to say, burning and bloating and shedding and pressing against their limits, enormous and unstable and temporary, in the way that all the most spectacular things are temporary, and you, wherever you are tonight, are made of the work they did. The atoms moving through your body right now, the slow breath you are taking in the dark, these were made in the interior of dying stars of exactly this kind. You are the downstream consequence of millions of years of stellar evolution, a chain of stellar lifetimes and deaths stretching back into the early universe. The population 3 stars that may have been the most massive of all, the ones whose size we can barely theorize about because none survived to observe, they seeded the heavy elements that later stars incorporated, and those later stars seeded more. And somewhere along that chain of stellar generations, the atoms that make you were forged and scattered and gathered again. You are not separate from this story. You are at the end of it so far. Back at the beginning of tonight, we asked a question that sounds straightforward. What is the biggest star? And we found that the question has a fuzzy edge. The biggest by radius is probably Stephenson 218 if you trust the distance assumption, which you probably should not trust entirely. The most trustworthy large radius belongs to WOH G64, its distance pinned by the known geometry of the large Magellanic Cloud. The most massive is R136A1, though its own number came down in 2022 from around 265 to around 196 solar masses, and even the mass champion could not escape the pattern of revision. And the reason none of them can get much bigger is the Eddington limit, that clean and unforgiving line where a star's own light becomes its own demolition crew. All night we have been circling toward that. If you have been drifting in and out, that is perfectly fine. The giants are still out there. The knowledge will still be here when you wake. And if you followed every measurement and every revision and every contested distance assumption all the way through, I hope it gave you something to hold lightly in the dark. A sense of how large the universe is willing to go, and a sense of how even its most extreme objects are temporary and cycling and ultimately, in the most long-run possible view, generous. If tonight felt like good company, a quiet like or a subscribe, would mean a great deal. Small creators like me rely on your support to keep these slow journeys going. And if you would like to leave a thought before you drift off, I would love to know where you are listening from tonight and what time it is in your corner of the world. Whether it is the middle of the night in a northern winter, or the early hours of a southern summer, or somewhere in between, I hope the dark is quiet and the thought of those enormous dying stars out there in Canis Major and Cephei and the large Magellanic Cloud is somehow, in the way that true and strange things sometimes are, a comfort rather than a weight. The stars are enormous and temporary and made of the same material you are, and that is a good thing to carry into sleep. Calm mind, clever dreams. I'll be here tomorrow night.